How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
Imagine standing on a beach on a clear summer day. You close your eyes and feel the warmth on your face. That heat, traveling 93 million miles through the vacuum of space, feels gentle, almost loving. We take it for granted. But if you were to trace that warmth back to its source, you would not find anything gentle. You would find a violence so profound it defies human comprehension. You would find a celestial furnace crushing atoms together, with enough force to threaten the very fabric of matter. For 70 years, humanity has been obsessed with a singular, audacious idea. We want to take that terrifying cosmic violence, shrink it down, and put it inside a box on Earth. We call it nuclear fusion. It is the dream of infinite carbon-free energy. It is the promise of saving our planet. But every time we think we have caught the star, it slips through our fingers. Why is it so hard? How does nature actually build a star? And what are the simple, unbreakable rules that keep the ultimate power source just out of our reach? Today, on First Principles, we are going to find out. To understand why fusion is the ultimate prize, we have to look at the energy reality we live in right now. Almost everything we do, every light switch we flick, every car we drive, every server farm that powers the internet, relies on burning things. We burn coal, we burn oil, we burn gas. We are essentially setting fire to the fossilized remains of ancient plants and animals. It is dirty, it is finite, and it is cooking our atmosphere. Then there is the other option we already have: nuclear fission. This is what powers the nuclear plants we see today, with the cooling towers and the steam. Fission is powerful, but it has a PR problem and a waste problem. It works by taking very heavy, unstable atoms like uranium and splitting them apart. When they split, they release heat, but they also leave behind shattered atomic fragments that stay radioactive for thousands of years. It is a messy divorce of particles. Fusion is the opposite. It is not about splitting things apart. It is about coming together. It is the marriage of atoms. If you can take the lightest, most abundant stuff in the universe, hydrogen, and smash two atoms of it together so hard that they fuse into one new atom, you get helium. You get a balloon gas. And in that moment of joining, you release a staggering amount of energy. No carbon, no long-lived radioactive waste. And the fuel, you can get it from seawater. A single glass of heavy water, derived from the ocean, could provide as much energy as a barrel of oil. It sounds too good to be true. And for the last half-century it has been, because while the concept sounds elegant, the execution is a nightmare of physics. To understand the nightmare, we have to go back to the beginning. We have to look at the problem the way the pioneers of this field did in the mid-20th century. In the 1950s, there was a sense of boundless optimism. We had unlocked the atom to build bombs, and we assumed that taming it for power would be a simple engineering cleanup job. There was a famous experiment in the UK called Zeta. In 1958, British scientists announced they had achieved fusion. They built a machine, fired it up, saw neutrons coming out, and thought, "We did it." The newspapers went wild. They claimed we would have infinite power within a few years. They were wrong. The neutrons were not coming from stable fusion. They were coming from instabilities in the plasma. They had been tricked by the complexity of the matter they were trying to control. This moment was the first hard lesson in the history of fusion. It is not enough to just make things hot. You have to control them. And controlling the substance of a star is the hardest engineering challenge our species has ever undertaken. So, let us strip away the shiny machines and the billions of dollars of funding and ask the first principle question. Why is fusion so hard? Why can we not just shove two atoms together? The answer lies in the fundamental personality of the atom itself, specifically the nucleus. The nucleus is the heavy center of the atom. It contains protons and neutrons. Protons have a positive electric charge, and if you remember your high school physics, you know that like charges repel. Imagine you are holding two incredibly strong magnets. You try to push the north pole of one against the north pole of the other. As you get them closer, you feel a resistance. The air between them feels thick, like a spring. The harder you push, the harder they push back. If you let go, they fly apart. Now imagine those magnets are atomic nuclei, and imagine the force pushing them apart is not just strong, but ferociously mind-bogglingly strong. This is the Coulomb force. It is the electromagnetic shield that every atom uses to protect its personal space. The entire universe is built on this repulsion. It is the reason you do not fall through the floor. The electrons in the atoms of your shoes are repelling the electrons in the atoms of the floor. Matter likes to keep its distance. To make fusion happen, to get that free energy, you have to overcome that repulsion. You have to push those two positive nuclei so close together that they touch, because if you can get them to touch, something magical happens. A different force takes over. This is the strong nuclear force. It is the strongest force in nature, but it has a catch. It has incredibly short arms. It only works at extremely tiny distances. Think of it like Velcro. Velcro is incredibly strong, but only if the two sides are actually touching. If they are even a millimeter apart, the Velcro does nothing. So, the game of fusion is a game of chicken. You have the electromagnetic force acting like a powerful spring, pushing the atoms apart, and you have the strong nuclear force acting like Velcro, waiting to snap them together. You have to overcome the spring to get to the Velcro. This barrier, this hill you have to climb to get the atoms close enough to fuse, is called the Coulomb barrier, and climbing it requires energy, massive amounts of energy. In our daily lives, we impart energy to things by heating them up. Temperature is really just a measure of speed. The hotter something is, the faster its atoms are jiggling and bouncing around. If you heat a gas, the atoms zip around like billiard balls on a table. So, the logic goes like this. If we want the atoms to crash into each other hard enough to overcome the magnetic repulsion and stick together, we need them to be moving fast, incredible fast. We need to heat them up. But we are not talking about the temperature of a kitchen oven. We are not even talking about the temperature of the surface of the sun. To make fusion happen on Earth, we need temperatures of 150 million degrees Celsius. That is 10 times hotter than the core of the sun. Why do we need to be hotter than the sun? Because the sun has a massive advantage over us: gravity. The sun is so incomprehensibly heavy that its own gravity crushes its core with immense pressure. That pressure forces the atoms closer together, so they do not need quite as much heat to fuse. On Earth, we do not have the gravity of a star. We cannot build a machine that weighs as much as the sun, so we have to compensate. We have to trade pressure for temperature. We have to make our fuel so hot that the sheer violence of the collisions overcomes the lack of gravitational crushing. But here is where the engineering nightmare begins. When you heat a gas to 150 million degrees, it stops being a gas. The electrons get stripped away from the atoms. The matter turns into a soup of charged particles. This is the fourth state of matter, plasma. Plasma is not like a gas. It is electrically charged. It conducts electricity, and it is wild. It does not want to sit still. It wants to expand, to twist, to cool down. It is like trying to hold a handful of living angry jelly. And this brings us to the container problem. If you have a substance that is 150 million degrees, what do you put it in? If you put it in a steel box, the steel instantly vaporizes. If you put it in diamond, the diamond vanishes. There is no physical material in the known universe that can touch this plasma without being destroyed. And even if the wall survived, the moment the plasma touched the cool wall, it would instantly lose its heat and the fusion reaction would die. So, we have a substance that cannot be touched. How do you hold something that you cannot touch? You have to build a cage not made of matter, but made of force. This leads us to the most iconic machine in the quest for fusion. The tokamak. It sounds like a creature from a fantasy novel, but it is a Russian acronym. It looks like a giant metal donut. Inside the donut, there is a vacuum, and wrapped around the donut are massive, superconducting electromagnets. Remember that plasma is made of charged particles, and charged particles react to magnetic fields. If you tune the magnets just right, you can create a magnetic field that spirals around the inside of the donut. The particles of the plasma will latch onto these magnetic field lines and spiral along with them. Ideally, the plasma flows in a circle, floating in the middle of the vacuum chamber, never touching the walls. It is suspended in a magnetic bottle. This is the approach taken by ITER, the massive international experiment currently being built in France. It is one of the most complex machines ever designed. It involves thousands of scientists, endless negotiations, and magnets so powerful they could lift an aircraft carrier. But the plasma fights back. As we heat it up, it creates its own magnetic fields. It develops turbulence. It wobbles. Imagine trying to squeeze a long balloon with your hands. As you squeeze one part, another part bulges out. The plasma is constantly trying to escape the magnetic bottle. For decades, this has been the dance. We build bigger magnets, better computers to control them, and deeper understandings of plasma physics. We manage to hold the plasma for a second, then 10 seconds, then a minute. We are inching closer to the goal. But there is another way. If you cannot hold the plasma for a long time, maybe you do not need to. Maybe you just need to be fast. This is the second great approach to fusion: inertial confinement. If the tokamak is a slow burn, like a furnace, inertial confinement is an internal combustion engine. It is a series of tiny explosions. The most famous example of this is the National Ignition Facility, or NIF, in California. Instead of magnets, they use lasers, the world's biggest lasers. They take a tiny pellet of fuel, about the size of a peppercorn. This pellet contains the hydrogen isotopes. They place it in the center of a giant sphere. Then, they fire 192 massive laser beams at it simultaneously. For a fraction of a billionth of a second, that pellet is subjected to more power than the entire U.S. electrical grid produces. The outside of the pellet explodes outward, which, thanks to Newton's third law, drives the inside of the pellet inward. The fuel is crushed. It is compressed to a density 100 times that of lead. For a brief, shining moment, the conditions inside that peppercorn match the conditions inside a star. The atoms fuse. Energy is released. In late 2022, the team at NIF made history. For the first time ever, they got more energy out of the reaction than the laser energy they put into the fuel. It was a breakthrough. It proved that ignition is possible. But, and there is always a but in fusion, The engineering reality is sobering. The lasers are inefficient. They take a long time to cool down between shots. To make a power plant, you would need to do this 10 times a second every second for years. We are doing it once a day. So we have the tokamak, the magnetic donut, trying to hold the hot soup steady, and we have the laser approach, trying to crush the fuel before it knows what hit it. Both are incredibly difficult. Both are forcing us to push the boundaries of materials science, supercomputing, and quantum physics. But now I want to take you deeper. We have talked about the magnets, the lasers, the heat, and the pressure. We have talked about the Coulomb barrier, that mountain the protons have to climb to fuse. But if we look strictly at the classical physics, if we treat protons just like tiny billiard balls, something does not add up. When astrophysicists first calculated the temperature of the Sun, they got a number, roughly 15 million degrees at the core. Then they looked at the strength of the Coulomb barrier. They calculated how much energy a proton needs to overcome that repulsion and touch another proton. The numbers did not match. The Sun is not hot enough. According to classical physics, the protons in the Sun do not have enough energy to climb the hill. They should get part of the way up, run out of steam, and roll back down. The repulsion is too strong. The temperature is too low. If the universe ran on the physics of billiard balls, the Sun would not shine, fusion would be impossible, we would not exist. So, how does the Sun work? How is it burning right now if it is not hot enough to fuse? The answer reveals the true, spooky nature of our reality. It brings us to the first principle that underpins not just fusion, but the stability of all matter. It is called quantum tunneling. You see, up until now, we have been picturing the proton as a hard little sphere, like a marble. But at the quantum level, that is not true. A proton is not a thing at a specific place. It is a wave. It is a smear of probability. Heisenberg's uncertainty principle tells us that we cannot know exactly where a particle is and how fast it is moving at the same time. The proton has a position, but that position is fuzzy. It is a cloud. Imagine the Coulomb barrier, that force pushing the atoms apart, as a high brick wall. A classical marble rolls up the hill toward the wall, loses speed, and rolls back. It cannot get over. But the quantum proton is not a marble. It is a wave, and that wave hits the wall. Most of the wave bounces back. But because the position of the proton is a probability cloud, a tiny, tiny tail of that wave extends through the wall to the other side. There is a small, but non-zero chance that the proton is actually on the other side of the barrier, without ever having climbed over the top. It is as if you threw a tennis ball at a garage door, and 1 out of every billion times, the ball did not bounce back, but simply appeared on the other side of the door. Leaving the door intact, it teleported through the barrier. This is quantum tunneling. The protons in the Sun are not smashing through the barrier by brute force alone. They are cheating. They are tunneling through the electromagnetic wall to get to the strong force on the other side. This probability is incredibly low. For any given proton in the Sun, the chance of this happening is vanishingly small. A single proton might bounce around the core of the Sun for billions of years before it successfully tunnels and fuses. But the Sun has a lot of protons. So many that, even with those terrible odds, enough tunneling events happen every second to light the solar system. This is the unseen giant. The Sun is a quantum machine. It is a slow-burning fusion reactor that relies on the fuzziness of reality to function. Now, think about what this means for us, trying to build a reactor on Earth. We cannot rely on the slow burn. We cannot wait billions of years for our fuel to fuse. We need power now. We need a reaction rate that is millions of times faster than the sun's core. This explains why we need such extreme temperatures. We need to increase the probability of tunneling. We need to slam those protons together so frequently and violently that we force the quantum dice to roll a double 6 over and over again instantly. We are trying to outperform the sun. We are trying to take a process that nature designed to be slow and steady and compress it into a high-speed, high-density fury. So where does this leave us? We have deconstructed the magic. We know that fusion is not just bottling a star. It is a war against the Coulomb force. It is a dance with the instability of plasma. And it is a game of chance played with quantum probabilities. We understand the principles. We know the math. The physics is sound. The challenge that remains is one of engineering and materials. It is about building magnets that can hold the force of an aircraft carrier without bending. It is about creating wall materials that can withstand the bombardment of high-energy neutrons without turning into brittle dust. It is about breeding our own fuel, tritium, inside the reactor walls, because it is so rare in nature. The skeptics will say that fusion is always 20 years away, and looking at the history, it is easy to see why. The goalposts keep moving because as we solve one problem, nature reveals a new layer of complexity. But think about the journey we have taken to understand this. We started with the simple desire for warmth and light. We looked at the sun and asked, how? That question led us to discover the nucleus. It led us to the strong force. It led us to the realization that matter is not solid, but probabilistic waves. It forced us to build the most complex machines in history, just to mimic what happens in the heart of a star. Fusion is the ultimate test of a civilization's maturity. It requires us to master the very smallest scales of the universe, to unlock the largest power source imaginable. It requires international cooperation, generational patience, and a stubborn refusal to accept the limits of nature. We are trying to light a fire that does not want to be lit, a fire that requires us to cheat the classical laws of physics. When, not if but when, we finally flip the switch and that plasma holds steady, delivering a stream of clean energy to the grid, it will not just be an engineering victory. It will be the moment we finally graduated from burning dead plants to wielding the primal fire of the cosmos. We will have looked at the wall that separates us from the infinite, and like the proton, we will have found a way to tunnel through. The universe runs on fusion. It is the baseline power source of reality. We are just finally learning how to plug in.
You've been listening to First Principles. Until next time, stay curious.